Hello all, welcome to the Predictive Analytics Regression and Classification course. Today we are going to, this is lecture 3 and part B. Today we are going to discuss some aspects of the Gauss-Markov theorem. Now, in the regression model, we will start with the standard regression model where the vector of inputs is a design matrix of X of order n and p, where n is the number of samples, and p is number of predictors. So, and y is the response vector. Okay, so this is our model, y equal to x beta plus epsilon. So, and our response vector y is a vector of size n, here it is, and is a standard model. Now onwards we will consider X matrix is our design matrix and number of sample is greater than P, because if the number of sample is greater than P, then X transpose X will be a P cross P matrix, and since it will be full rank matrix, X transpose X will be full rank matrix, and we will have a unique solution. So we will consider X design matrix, typically considered as a deterministic, and n is greater than P. Now epsilon, also known as error or residual, for all samples are considered as a random variables, and on these random variables we assume three assumptions. First, expectation of epsilon I is equals to 0. Second, variance of epsilon I is sigma square for all I. For all samples, the variance of residual is sigma square, and this assumption typically known as homoscedasticity. And the third assumptions that we are making are known as covariance of epsilon I, epsilon j equal to 0. This is coming from the independence assumption, that is ith sample and the jth sample, they are independent of each other, and that assumption gives us the assumption that covariance of epsilon I and epsilon j 0. Now that means this we can write it in a matrix notation where expectation of epsilon is 0, a vector of 0, n vector of size n, where all elements are 0, and then we can join the second assumption and the third assumption a little bit. We can join this second and third assumption, and then we can make this assumption as with the matrix notation. It will be covariance of epsilon is sigma square by in. So that means it's a diagonal matrix so basically capital sigma will be all sigma square, all the diagonal elements are sigma square, and all the off diagonal elements are all 0. Okay. Now, what does it mean? What is the implication of this assumption? What is the implication of this assumption? The implication means it induces a distribution on the response vector y. Because expectation of y is equal to, we can say, if we take expectation of y, x typically we are considering a deterministic, beta in a classical setup we consider as a unknown constant. So that means x beta plus expectation of epsilon. Now expectation of epsilon is 0. That is our under assumption. This is the assumption under this assumption. So that means expectation of y is equal to x beta. And the covariance of y is equal to sigma square by in. So this is our covariance matrix of order n cross n. Typically diagonal matrix with all off diagonal are 0. Now, one important thing I would like to make, that we have not made any distributional assumption on epsilon yet. We have only assumed that the residual or errors are random variable. That means they have a distribution, they do have a distribution, but they do not and they have a mean vector, they have a covariance vector, but we are not making any assumption about whether epsilon follow a multivariate normal or any other distribution. We will introduce this assumption later. We will introduce assumption later as we require. Okay. Now, what is the implication? We will continue on this. What is the implication of considering this assumption? What is the expected value of Cy if C is a constant? Now, we already have found expected y is equal to x beta, then expected value of Cy will be expected value of C into x beta. Now, this is an interesting thing because now consider ordinary least square estimator, OLS estimator of beta. So this is our OLS estimator of beta, correct? This is our OLS estimator of beta. Now, what is, if you see x transpose x inverse x transpose, this part is deterministic part, but y is the non-deterministic part. It's a response, and then that means we take expected value of beta hat, and then in beta hat we replace the x transpose x, the formula, the analytic form, x transpose x inverse x transpose y, and then that gives us x transpose x inverse x transpose is a constant, so it will come out of the expectation. So what we have is here is expectation of y, and then expectation y is x beta. Now interestingly, this is x transpose x inverse x transpose x, which will be identity matrix. So we left with beta. So what does it mean? That OLS estimator beta hat is an unbiased estimator of beta. So this is a OLS estimator is an unbiased estimator of beta. This is a very important finding. Now, suppose we are interested in some linear combination of the regression coefficients, some C transpose beta. What is the interpretation of this? We will come to that. We will do an example and then it will become much more clear to you. So, the result says then unbiased estimator for C transpose beta is simply C transpose beta hat, because effectively expected value of C transpose beta hat is, if you just take C transpose out of the expectation, then it will be like C transpose of beta hat, which is beta, so C transpose beta hat. So this is right away C transpose beta hat is an unbiased estimator. Now suppose C is equal to x naught, a test point. Then we are interested in finding f of x transpose beta, x naught transpose beta, that is my target. So all I have to do that x naught transpose beta hat is my unbiased estimator, is an unbiased estimator for the test point C equal to x naught. So this is an interesting findings that we got. Now another example we will do, that suppose there are 4 treatments, treatment 1, treatment 2, treatment 3 and treatment 4. These are the 4 treatment, and we consider the model y equal to beta naught plus beta 1 times treatment 1, beta 2 times treatment 2, beta 3 times treatment 3 and an epsilon. Okay. Now our regression coefficient beta equal to beta naught plus beta 1, beta 2, beta 3. This is the regression coefficient. Now what is treatment 1? So what we have done, as usual, as discussed last time, this is one hot encoding. So if I need to figure out what would be the expected value of y when it is treatment 1, what I will do, I will put in this case treatment equal to 1 and here I will put zeros. Now if I need to calculate what would be the expected value of y if I am looking for treatment 2, then what I will do, I will make this one as 0, and for treatment 2 I will make treatment 2 as treatment 1. And treatment 3 will be 0. So the model will be, so the solution will be beta naught plus beta 2. And in this case, it will be beta naught plus beta 1. Now if you are interested in expected value of y when, if it is treatment 3, then same way I will take treatment 3 as 1 and take treatment 1 as 1 and 2 as 0, and I will make treatment 3 as 1, and that will give me beta naught plus beta 3. Now if I am interested in beta expected value of y when it is treatment 4, then what I have to do, I will put all treatment 1 equal to 0, treatment 2 equal to 0, treatment 3 equal to 0, and intercept on beta naught is itself will give me the expected value or expected level of y if we are in treatment 4. Now suppose we are interested in to measure the difference between treatment 1 and treatment 3. So this is what we are interested in. What is the difference between beta 1 and beta 3? Beta 1 is the measure of difference 1. So basically this is what we want to do, expected value of y given treatment 1 minus expected value of y given treatment 3 Now what is y given treatment 1? Y given treatment 1 is beta naught plus beta 1. Beta naught plus beta 1 minus, what is y given treatment 3? This is beta naught plus beta 3. Beta naught plus beta 3. So what we left with? Beta 1 minus beta 3. So if I am interested in measuring the difference between the expected level for treatment 1 and expected level for treatment 3, then basically the difference between beta 1 and beta 3 is good enough. If I just measure the difference between beta 1 and beta 3, that would be good enough. So for that, what we will do, we will simply consider C to be 0, 1, 0, minus 1. You see, if you take C transpose beta, and then what you will get? Beta 1 minus beta 3. Now Gauss Markov theorem tells me that if I take C transpose beta hat, just take the beta OLS estimator beta hat, multiply with this C, or take the dot product of the C with the C and the beta hat. That will be best linear unbiased estimator for the effective difference between treatment 1 and treatment 3. So this will be C transpose beta hat is best linear unbiased estimator for C transpose beta, which is beta 1 minus beta 3 in my case. So there are these kind of very nice things you can do for using Gauss Markov theorem. Now if you have any other linear estimator, say theta tilde A transpose Y is unbiased estimator for C transpose beta, then you can show expected value of A transpose Y is equal to C transpose beta, and variance of C transpose beta hat is less than equal to variance of A transpose Y. So this is what typically called the Gauss Markov theorem. So that means essentially OLS estimator, estimate of the parameter beta, is the smallest variance, have the smallest variance among the linear unbiased estimates. So this is the main crux of the Gauss Markov theorem, and that makes our life very simple. All you have to do that, if I need a good, so if I am interested in finding an estimator for C transpose beta, which turns out to be very useful functional form, and then what all I have to do, I have to just find a OLS estimator and then multiply the OLS estimator beta hat with C transpose. That will ensure that this will be best linear unbiased estimator for my target functional form C transpose beta. Now what is it? There are certain things to note here. If you consider mean square error for an estimated theta tilde, suppose theta is your target parameter and theta tilde is your estimator that you are using to estimate. Now mean square error is simply expected value of theta tilde minus theta whole square. So you can write this as variance of theta tilde plus expected value of theta tilde minus theta whole square, which is a bias. Now, so basically variance plus bias square. Now Gauss Markov theorem implies that least square estimator has smallest mean square error among the all linear estimator with no bias. Now bias here is 0. So among all the unbiased estimator, the least square estimator and its C transpose beta hat has the least mean square error. However, there may well exist a biased estimator with smaller MSE. For example, Ridge estimator or James-Stein shrinkage estimator of beta trade a little bias for reduction of variance, and its MSE are lower than the best linear unbiased estimator. So you can find the estimator. Though Gauss-Markov theorem is very good, strong theorem, it shows that among the class of all linear unbiased estimator, it has the minimum mean square error, it has the minimum variance, but estimator like Ridge estimator, James-Stein estimator, you can trade a little bit bias, you can induce a little bit bias, but you will, if you can reduce variance rate significantly, then overall mean square error can go significantly reduce. And in that case, what will happen, that mean square error is even lower than the best linear mean square error of the best linear unbiased estimator. So sometimes you can come up with a slightly biased estimator which will have a better mean square, in a lower mean square error than the Gauss-Markov estimator. However, among the class of all unbiased estimator, Gauss-Markov estimator is the best. So we will stop now. Thank you very much. Let's join to the next video.